Large language models, or LLMs, have made incredible strides in handling all sorts of natural language tasks, from writing essays to answering complex questions. But there's a big catch. They require massive amounts of computing power, especially when dealing with long prompts. This paper, titled PIS, Linking Importance Sampling and Attention Mechanisms for Efficient Prompt Compression, introduces a new way to make these models more efficient by compressing prompts without losing key information. At the heart of the issue is that LLMs generate responses by processing sequences of tokens, which are basically the building blocks of text like words or parts of words. As these sequences get longer, the computational cost skyrockets. For example, memory usage grows quadratically with the sequence length, and processing time increases linearly. This makes it tough to use LLMs for tasks that need deep reasoning, like planning or problem solving, because they can become slow and resource intensive. Existing methods for prompt compression fall into two main categories. First, there are generative approaches, like the one in LLM Lingua, which use additional language models to rewrite or summarize the prompt. These can be effective but add extra computational overhead, making them expensive to train and run. Second, there are heuristic methods, such as selective context, that simply cut out tokens based on simple rules or surface-level metrics. The problem with these is that they don't consider how LLMs actually work internally, so they might remove important information that the model relies on, leading to poor performance. To address these shortcomings, the authors propose a framework called prompt importance sampling, or PIS. This method is designed to compress prompts in a way that's more aligned with the inner workings of LLMs. Specifically, it draws on attention mechanisms, which are a core part of how these models process information. Attention scores help the model focus on the most relevant parts of the input, so PIS uses these scores to identify and keep the most important tokens. PIS operates on two levels: token level and semantic level compression. At the token level, the framework quantifies the importance of each token by analyzing the attention scores from the LLM's hidden states. This means it looks at how much weight the model gives to each token during processing. To make this adaptive, they use a lightweight reinforcement learning network, just 9 layers, to decide which tokens to keep or discard. This RL network learns to sample tokens in a way that maximizes the compressed prompt's effectiveness, ensuring that the most salient information is preserved. Moving to the semantic level, PIS introduces a Russian roulette sampling strategy. This is inspired by probability techniques where you decide whether to include or skip certain elements based on their importance. In this case, it's applied to sentences, allowing the framework to sample entire sentences based on their overall relevance. This helps maintain the prompt's meaning at a higher level, beyond just individual tokens, which is crucial for tasks that rely on context and structure. The authors back this up with a solid theoretical foundation. They establish a measure-theoretic basis for prompt compression, essentially formalizing how to balance token reduction with semantic preservation. This means they're not just hacking together a method. It's grounded in math that aligns with how LLMs compute and generate responses. To test PIS, the researchers conducted comprehensive evaluations across various benchmarks in different domains. The results show that PIS achieves state-of-the-art performance in compression. For instance, it significantly reduces the prompt length while maintaining high accuracy in tasks like reasoning and question answering. In some cases, it even improves efficiency by optimizing how the context is structured, making the LLM faster and more effective. One key advantage of PIS is its efficiency. Unlike methods that require training a separate model on compressed versions of the input, PIS only needs a compact RL policy network. This makes it ultra-low loss and high performance, as illustrated in the paper's Figure 1, which compares it to traditional approaches. Overall, this work advances the field of prompt engineering by providing both a theoretical framework and practical tools for managing context in LLMs. It answers two main research questions: how to get better compression without relying on extra generative models, and how to make compression work in harmony with the LLM's internal mechanisms. By focusing on importance sampling through attention, PIS paves the way for more accessible and efficient use of large language models in real-world applications.